All right, the video is being recorded now. So good afternoon, everyone. This is lecture 21, Deformation Gradient in Continuum Mechanics. So the agenda for today, we will be quickly recapping as to what we did last time in terms of deformation gradient. So a recap of deformation gradient tensor. And then we will understand how to use this deformation gradient tensor. So use and we'll define our strain tensors using this. So remember that the aim here is to be able to quantify deformation, because if you remember in the previous chapter, we talked about stresses. We talked how external forces on a certain body can result in the internal stressing of the body. And now we are trying to understand how to quantify the deformation of the body, which is in most cases caused because of these external forces which are causing internal stresses. And then ultimately, once we have got mathematical way to quantify our deformations, then we'll be in a position to link the stress with the strain using our Newtonian laws of mechanics. Okay, so today we'll define our strain tensor, which ultimately will be used to quantify our deformations in the future. So let's quickly recap as to what we did last time. In the previous lecture, I started with a reference configuration. So reference configuration is a configuration which the body has taken at t equals 0. That is what the body was, the situation that the body was at t equals 0. And then after some time, we deform the body due to some external forces, and then we have a current configuration, or what we called it was the deformed configuration. So we'll call the reference configuration as the undeformed configuration. Right. So we have the undeformed configuration and the deformed configuration, and then we took 2 points, a point P and a point Q, and we were trying to understand what's happening around point P. So our aim was to quantify the deformations around point P, or we can say that we are trying to understand how to quantify deformation at point P. So if I can take arbitrary points Q around a particular point P and draw these vectors, in this particular case, it's this vector dx, d capital X, then if I can understand what happens to this vector in the deformed configuration, that is my small p and small q denote the deformed positions of my points capital P and capital Q. This we denote as d small x vector. So if I can do this, if I can develop a relation, if I can say I can write my dx as some function of d capital X, where d capital X is always defined from P to some point Q around P. If I can do this for all possible d capital X values, then I have quantified my deformation completely around point capital P. And that's what the aim was. So we did that, and we were able to come up with a relation where we said our d small x is an tensor F dot d capital X, where this tensor F was called the deformation gradient tensor. Okay. So this F was nothing but Fia was nothing but xi comma a, xi comma a, or del xi by del capital XA, which we had written in the expanded form as del small x1 by del capital X1, del small x2 by del, del small x1 by del capital X2, and so on till del small x3 by del capital X3. Okay, so it has two free indices, I and A. So it is a second order tensor, as we already know. Okay, so what we've done is we have been able to, if I can tell you what this tensor is, then you have all the information you need to be able to quantify the deformation around the point P. And if I tell you what this tensor is for all possible points in the undeformed configuration in the body, then you have the information about the complete deformation of the body. Okay, so that's what we did last time. And this time I will show you how to use this tensor F to define our strain tensor. All right. So a measure of deformation, one measure of deformation is d small x squared minus d capital X squared. We will use this in the future for certain reasons, but for now all we want to do is we want to understand how this difference in the squares of the length of the undeformed of the deformed vector minus the undeformed vector square, how does this value change with what's the difference between these values in terms of our deformation gradient tensor. So this, the square of the vector in the deformed configuration, if I just go back and show you, so it's talking about this length from small p to small q, which is this length. So if, sorry, it's not clear, then I'm talking about this vector d small x. I would want to know the square of the length of this vector. So the square is nothing but d small x vector dot d small x vector, and the d capital X magnitude square is written as d capital X vector dot d capital X vector. And we can also write this in the initial notation, which is what we prefer, as d small xi minus d capital X a d capital X a. Now, I mentioned last time that we use capital indices for the material coordinates or the undeformed configuration, whereas we use the small alphabets for our Eulerian description or the deformed configuration. Okay, you can choose to use small indices for the capital X's as well. It's your choice. Now, based on the relation that we developed in the last lecture, that is, we wrote dxi is xi comma a d capital X a. So using this relation, I can write this dxi dxi as right. So I've written the first dxi as xi comma a dxa. I've written the second dxi as xi comma b dxb. The reason I've chosen a and b as separate indices is because they are repeated or free indices here. So we should make sure that they do not appear more than 2 times. Otherwise, it has no meaning. Okay, so we choose a and b separately as 2 different indices. So we can rearrange these terms. Sorry, I've made a mistake in the term above here. It should be dxa dxa. So I can write this as delta AB dxa dxb. So now you see that we are making full use of Kronecker delta here. Earlier we had understood how to use it by using the substitution property and simplifying things. Now we are going in the other direction. We are writing dxa dxa as delta AB dxa dxb. So that's the next step in learning we are using, is this to write to develop a form which is more convenient for us in this case. So this now we can simplify as xi comma a xi comma b minus delta AB times dxa dxb. So this we write as CAB minus delta AB. Okay, so this quantity C here is called the Green's deformation tensor. So you see that we are defining many new terms here. So it's just a definition. We define this term C, which is written as the product of F transpose F as the Green's deformation tensor. And you can see that this xi comma a is nothing but fia, and xi comma b is nothing but fib, and this is written as, this is defined as CAB. And this in the symbolic notation can also be written as, I mean, if you want to really see how it's done, so you can write this as F transpose of AI times FIB. And you can see that the index I and I are now in the right order. So we can write this as F transpose F is equal to C. So the Green's deformation tensor is, C is defined as F transpose F. Okay, so it's just another term that we have defined using the deformation gradient tensor F. And we simplify this further, we define another term. So this CAB minus delta AB is written as twice EAB and this twice EAB is called the Lagrangian finite strain tensor. Okay, so this is our first strain tensor that we have defined. Okay. So a quick summary of what we have done. So we started with this quantity called d small x squared minus d capital X squared. So it's a measure of deformation, as we'll see later. It's just one quantity that tells us the difference between the squares of the length of the vectors in the undeformed and the deformed configurations. So this we write as dxi minus dxa dxa. In the initial notation, we simplify things further using our definition of the deformation gradient tensor. So we write d small xi in terms of d capital X a, and then we define this quantity Green's deformation tensor as the product of F transpose F, and then we define this C minus I as twice of E, which is called the Lagrangian finite strain tensor. So that's the overall summary of the steps that we have performed to define our first strain tensor, which is called the Lagrangian finite strain tensor. Alright, so in the symbolic notation, we define this we define twice of E as C minus I, and our C was defined as F transpose F. Okay, so this factor 2, as you will see, is purely for algebraic purposes. So this factor of 2 gets cancelled out. So that's the reason we have define C minus I as twice of E rather than just E. But this factor of 2 is just for convenience. But it is as a part of its definition. All right. So if I go back and see the first step and the last step, then this quantity, which is d small x squared minus d capital X squared, is finally written as twice EAB dxa dxp. So I'll write that again. Okay, so we can rearrange the terms. So we can write dxa times twice EAB times dxp. So you can see this now the indices are in the right order. So this means that this term can be written as dx vector dot twice E dot dx vector. So remember that E is a second order tensor here, which is called the Lagrangian finite strain tensor. Okay, it's called Lagrangian because as you see that everything is written in terms of d capital Xa. So E is also defined in terms of capital X vector. Okay, so we can do the spatial, we can write a spatial form of this strain tensor. So what that means is, I won't do it here, I'll leave it for you to complete the steps. But what we do is, we start with the same thing. I'll write a 2 here. And then instead of writing this in terms of capital X, we try to write everything in terms of small x. That is, D capital XA, D capital XA. We try to write this in terms of small x's. So what we do is, so this D capital XA, if you remember, I mean, if I go back to the definition of our deformation gradient tensor, then D small x was F times D capital X. So we can define the, we can take an inverse on both sides. So we can define D capital X as F inverse times D small x. So what we have done is, we have in the first equation, we have left multiplied both equations by F inverse. Okay, so this helps us define D capital X in terms of D small x, it helps us define D capital X in terms of D small x. So I can write this D capital X A as F inverse of AI times D small xi, and I can write this F inverse of AJ D small xj. So you can complete the steps now. So you can rearrange the terms and so on, and finally simplify this. So if you get confused, please refer to the book. The book clearly carries out all the steps. And finally, what we get is, we are able to write this difference in the squares of the lengths as d small x times twice small e times d. Sorry. So this small e is called the Eulerian finite strain tensor. All right. So let me tell you how we define small e. So we define twice of small e as identity minus small c, where small c is called the Cauchy deformation tensor, and our small c is defined as F inverse transpose times F inverse. Yes, everything is the inverse of what we had defined earlier. So what we have done is a quick summary of what we have done till now. We have defined two strain tensors. One is called the Lagrangian finite strain tensor, which is E, which is small e. Okay, you can go back and refer to how they are defined in terms of our deformation gradient tensors. If I give you the deformation gradient tensor, you can calculate both these quantities at that point. Okay, you know that how they're used. You use them to write the squares of the difference in the lengths of two tensors. So the squares in the lengths of two vectors, the deformed vector and the undeformed vector. Resume it. Yeah. So now that we have defined these strain tensors, we must understand how a strain tensor can help us quantify the motion. I mean, what we have done is we've simply defined that mathematically, but we should get a feel of what they mean. Now, the next analysis that we do is we will try to understand how the angles between two vectors originating from point P will change as the body gets deformed. Let's start from a new page. So what we do is we take 2 points, well, 3 points now, P, Q, and R, and we draw two vectors. So one is D capital X superscript 1, and the other one is D capital X superscript 2. Similarly, so this is our undeformed configuration. Now we have the deformed configuration. So the vector small p to small q is called d small x1 superscript 1, and small p to small r is called d small x superscript 2. So our aim here is to understand how the angles between these vectors change and how they can be related to our strain tensor that we have just defined. So the way to understand the angles between two vectors is to take dot product, because if you remember, the dot product is vector length 1 times vector length 2 times cos theta. So we'll start with the quantity, call it 3, d small x1 dot d small x2. And what we'll do is we'll write this in terms of d capital X vectors. So the exercise is now you should be comfortable with that. So this is d small x I1 times d small x I2. Okay, so in the previous analysis, what we did was we started with d small x I, d small x I. So that means 1 and 2 were the same. So what we are doing now is a more generalized analysis than we did in the previous step. So the previous step will come out as a special case of this, because if we put 1 equals 2, that is, we assume that the angle between them is already 0, we'll get whatever we got in the previous steps. But it's worth going from specific to more general to understand things in a better way. Right. So now we can use the definition of the deformation gradient tensor and write d small xi1 as FIA d capital X 1A And I can write the second one as FIB D capital X to B. So I rearrange the terms. I write FIA as F transpose AI so that I can see the indices I next to each other, which helps me write the product. So this becomes D capital XA1 times CAB, the Green's deformation tensor as we defined it, and you have dx to b. Now this CAB, now if you remember, we defined twice of EAB as CAB minus delta AB. So I can write my CAB as a sum of twice EAB and delta AB. So now I can expand this. So this becomes so this is the first term, and this is the second term after we apply the substitution property of Kronecker delta. Now let's try to understand what happens here if our E, that is the Lagrangian finite strain tensor, is 0. So if EAB is 0, that is all the terms in this Lagrangian finite strain tensor, all the 9 terms are all 0. Right, so if EAB is 0, then the first term, that is this whole term, becomes 0. So what we get is d small x1 dot d small x2 is equal to d capital X A1 times, sorry, dot okay, so the dot product between d small x1 and d small x2, it's a dot product between d capital X1 and d capital X2. Okay, so that's what we get if EAB is equal to 0. Now I can also put, so this is a general case, if 1 is equal to 2, that is, if this 1 becomes equal to this superscript, the index, then what we get is d small x1 dot d small x1, that's the square of the length, is equal to square of the length of the d capital X1. So what this means is, so if this is the case, let's put it in words. So the length of line segments remain unchanged. So in the bracket I'll write, see this by substituting 1 equals 2. Okay, so if you substitute 1 equal to 2, then you can clearly see that the length of line segments remain unchanged. So what we are saying is, if you draw any line segment around point P, that line segment will retain its length. It will not get elongated or compressed. The length of the line segment will remain the same from the undeformed configuration to the deformed configuration if our E is 0. Now, what we also see, so if the lengths are the same, now let's not put 1 equal to 2. Now we already know that lengths are the same. So I can write my d small x1, d small x2 as the length d small x1, the length d small x2 times cos theta. Okay. If the lengths are the same, then what we see is that the angles are also the same. Okay. Since they are equal, so using this condition, the one that we have written, what we see is, let me write that in words. The angles between line segments, they also remain unchanged. So it's very interesting. So what we have seen is that if EAB is equal to 0, then the length of line segments which are being drawn from point P outwards are the same, and the angles between any two line segments drawn from point P are also the same. Now, if this is the case for all the points in the configuration, what do we see? Any guesses? So let me rephrase my question. So what sort of a deformation is it if at all the points, line segments emanating out of it have the same length, and the angles between any two line segments from that point are the same? What sort of deformation are we talking about in this case? Right, so the answer is that it's a rigid body displacement. So it's again easy to see that. Remember that we said that the motion can be split into two parts. One is rigid body displacement, where the body moves as a whole, so which is a sum of translation and rigid body rotation. So you translate the body, rotate it. That's a rigid body displacement, and the other part of motion is deformation. Okay. So in this case, what we see is that if EAB is 0, then the length of line segments, so if you take any 2 points in the body, join them, the lengths of those line segments will remain, I mean, of course, these 2 points are close to each other. The lengths of these line segments will remain same. That means no elongation on compression. And then the angles between any 2 line segments are also the same. They do not change. That means that the body at max can rotate. Because if you rotate a body as a whole, rigid body rotation, then the angle between any 2 line segments remain the same. The absolute angle may change, but the angle between line segments will still remain the same. So as a summary, what we see is that if EAB is 0, then the motion that we're talking about is rigid body displacement. So the corollary of that is that EAB contains the information about deformation at max. Okay. EA being 0, the body has simply a rigid body displacement. Okay, so now this is, so EAB is interesting to us because in this course, what we're interested in is the deformation and not rigid body displacement. So EAB, as we'll see later, will contain, so we will analyze this EAB or some form of strain tensor in more detail later. So what we have seen is that EAB contains information about motion, which is something other than rigid body displacement. So that is deformation, and that is what is interesting to us. Now, what we have seen is that EAB was written in terms of a deformation gradient tensor. So if I remind you again, so this EAB So this was C minus I, where the C was F transpose F. So EAB actually was this. So if I give you the value of F, the deformation gradient tensor, then you can use that to calculate the value of a Lagrangian finite strain tensor. Okay, so we can also write this capital E and small e. Of course, I mean the same analysis can be done for small e as well. It's just that we try to convert everything in terms of our Lagrangian coordinates. You can also do that in the Eulerian coordinates, that is small x, and then you will get the interpretation of small e, which is still the same. Okay? So small e being 0 means that the body only has rigid body displacement. Okay, so now what we'll do is we'll write capital E and small e in terms of displacement gradients. So let me remind you what displacement was. So if you have a point P and you have a point small p, then the displacement is defined as the vector u, which goes from a point capital P to small p. Okay. So u vector was defined as small xi minus capital Xi. And if we try to write everything in terms of capital X, then that's how we write it in the initial notation. Okay, so u is a function of capital X. So in the symbolic notation, we write this as u vector is a function of capital X vector, which is small x minus capital X, where we write the small x vector as a function of capital X vector. So that's the Lagrangian description of motion. Right. So let's use this to write our twice of EAB, which was F transpose F, which is F transpose is nothing but x I comma A, x I comma B minus delta. So that's in the initial notation. Okay. So what we do is we write this. Xi comma I. So what I can do in equation 1 here is I can differentiate this with respect to A. So what we get is, let me remove this symbolic form. Now capital X of I comma A, if you remember, now this is everything is differentiated with respect to capital XA, and that's the reason we used the capital indices for the capital letters, so that now it is clear that the differentiation is in terms of capital X. So what we are writing here is partial ui by partial capital Xa. Okay, so this term is nothing but our canonical delta IA. So what I'm doing is now I'm using this relation, and I'm trying to write my xi comma a as ui comma a plus delta ia. So the aim here is to get rid of our f tensor, or xi comma a and xi comma b, and write things in terms of the gradients of our displacement tensor, or displacement vector u. Okay, so that's the only thing we want to do here. So we can expand this form. So we have simply expanded the brackets and we get these right terms. Okay. So let's simplify these terms. Now this term, we can apply the substitution property of delta. So what we get is we get u b comma a, and then this next term, again we can apply the substitution property of delta. So we get u a comma b, and the second last term we can apply the property again, and we get delta ab, and there's a minus delta ab, so this term can be removed. So that's an extremely important relation that we have in this discussion. So we will use this. We'll start from this step later. And similarly, we can also write our Eulerian finite strain tensor. That is twice of that. So twice of E ij as u a comma I, u a comma j plus u I comma j plus u j comma. Right. So we'll get back to these in the next lecture. All right, so it's almost time now. So we'll what I'll do is I'll ask you to try example 461 from textbook, which is Mace and Mace, second edition. So please try it. It's a very good example. It helps you understand how to use these deformation tensor for a particular case of deformation that's been given to us. Okay, so we will stop here now, and I'll see you next week.